Hello students. Uh, in the previous video, we have talked about the sequences and summations. So in this video lecture, continuing to the previous one, we will be talking about the cardinality of the sets. We already know what is a set. We already know what is the cardinality of set. So in today's video, we will be talking about cardinality more detail. We will be talking about the countable sets, the countability, and we will talk about the computability. So starting formally for this topic, so basically what is a cardinality? You already know, if you remember from the previous classes. So if I have a set, right? So we have two types of sets. One is the finite set, and other set could be the infinite set. So what do I mean by the finite and what do I mean by the infinite set, right? So finite sets are sets with the limited with the countable number of elements, and infinite sets are the unlimited, or going on the uncountable set of the elements, but not exactly the countable and uncountable that what I am talking about. So let's just take one example. Say the number of subjects that you are teaching in your undergraduate program. So the set of the subject is finite. You might be teaching 20, 30, 40, 50,000 maybe. So they all are these all subjects are finite. So such set is called finite set. An infinite set, such for example, the the stars in the sky, right? So you cannot count it at once. That's why we are going to call it infinite. So they are never ending. They keeps on going on. Set of natural numbers starting from 1 2 3 4 5 6 and goes on, right? So such sets are called infinite sets. So remember, the finite sets are always countable, right? So finite sets are always countable, but the infinite sets may be countable and may not be countable, right? Not countable. So all the finite sets are countable. Infinite set may be countable, may not be countable. So if an infinite set is countable, we call it countably infinite set. And if a infinite set is not countable, we call it infinitely uncountable set, right? So let's see the formal definition now. So the cardinality, we all know the number of elements in a set, right? So the cardinality of a set A is equal to the cardinality of a set B. We denote it like this: if and only if there is a one-to-one correspondence or a bijection from A to B. What do it mean? So for example, if you have a set of even numbers, right? You have a set A, set of even number, that is 2 4 6 8 10 and so on, maybe up to 20 288, right? It's a finite set, for example. And then you have a set B, that is a set of odd numbers, that may be 1 3 5 7 9 and goes on, say for example up to 287, right? So these are two sets. Can we have a function that can map set the elements of set A to element of set B, such that this is an onto function? It's a bijection, one-to-one correspondence, one-to-one correspondence. So if we can formulate such function, right, then we say the cardinality of A is equal to cardinality of B. So you can see the number of elements in set A is equal to the number of elements in set B, if and only if, the condition is if and only if there is an one-to-one correspondence, right, a bijunction. Say for example there is a set, for example there is a set A is a set of again even number, but infinite even number, 2 4 6 8 and so on up to infinity. right? And then B is also a set of odd number 1, 3, 5, 7, so on, so on, so on, up to infinity, right? So can we still have a mapping? Yes, we still can map one-to-one mapping from A to B. If this, no matters uh, how many number of elements are in set A and how many number of elements are in set B, since they both are approaching to infinity, they both have the infinite number of elements, but still we can map, we can find a function that can map one to one element, one to one, that can perform one to one mapping, right? Like this. We don't know how many number, but we still can find a function that can map a set of even numbers to the set of odd numbers in a one-to-one manner, in a one-to-one correspondence, in a bijection manner. If this is true, then we say that the cardinality of set A is equal to cardinality of set B, right? If there is a, now let's see, if there is a one-to-one function, right, that is an injection function, right, from A to B. What does that mean? The cardinality of A is less than or the same as the cardinality of B, and we write it like this way. It's obvious if you remember from the functions. In an injection function, what happens there, there is the possibility that the elements in set A are mapping to the elements of set B. They may have more, I mean, one image may have more pre-images, right, if you remember from the definition. So that means elements, it's the possibility that both sets A and B have the same number of elements, or maybe set A has less number of has elements, or the cardinality of A is less than the cardinality of B, and that is represented like this, right? When A cardinality of A is less than or equal to B, and A and B have different cardinalities, right? We say that the cardinality of A is less than the cardinality of B, and we write it in like in this manner. So it should be very clear after this slide that the set may be finite, set may be infinite. If the set is finite, it is countable. If set is infinite, it may be countable, it may not be countable. How it is countable, that we are going to discuss in this video lecture, right? So when we call a set countable, set is countable only when there is one-to-one correspondence, or a bijunction function, or one-to-one function. If we can find a one-to-one function, then we can call, we can say that this set is countable, and then we say that the cardinality of both set are same, right? Okay, so let's see the definition of the cardinality now. A set that is either finite, that what I have explained earlier, a set that is either finite or has the same cardinality as a set of positive integers, that is z, that is represented with z plus, is called countable. So that's the definition of the countability. What is the countability or the countably infinite countable sets? Let's read it again. A set that is either finite, if the set is finite, then for sure it is countable, right? But if the set is infinite, then how we can say that it is countable or not countable? Then what? If a set or has the same cardinality as a set of positive integers. So set of positive integers, we already know that what is the set of positive integers? Z plus, that is what, 1, 2, 3, 4, and so on, so on, so on, up to infinity. So if, so for example, I have a set S with some elements in it, and I want to say whether this set S is countable or not, I can, if I can form a function that maps the set elements of set S to the set of positive integers, right, in a one-to-one manner, in a bijunction manner, then I will call this set S as a countable set, right? A set that is not countable is uncountable. So if we cannot find any such function that can map it in a one-to-one fashion, then we call it uncountable, right? So we'll see some of the example in few slides. So for example, the set of real numbers R is an uncountable set. I just gave you the example in the previous I mean, the previous slide, that set of stars in the sky is infinite. We already know that we have infinite stars in the sky, but still it is countably infinite. What do I mean by that? I already have a positive set of positive integer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 up to infinity. Can I count the stars in this fashion? And can I say star number one, star number two, star? Okay, set of stars. For example, set of stars, right? And then this set of star is also the infinite set. Can I map it the star to this function? Star number one, star number two, star number three, 4, 5, 6, 7, 8, up to infinity. If we can have one-to-one correspondence, we call it countably infinite. Countably infinite, right? Infinite set. So see the definition once again. If it is a finite set, it's definitely countable. And if it has the same cardinality as a set of the positive integer, then we call it a countable set. So in the previous slide, that's what I explained here. So if, even though the sets are infinite, if they can have a function that maps one-to-one correspondence, we say that the cardinality of these two sets is same. That's what it is referring here. It says if the cardinality of it, this set of star is equivalent to the positive integers, then it is countable. So we know that the positive integers are not never ending, so the counting of the star is never ending, so we can map them in a fashion. For example, the hairs on your body, so you might be not able to count it, but you can count that they are the hairs on your body may be infinite, but it is countably infinite. In some fashion you can count them, and then it becomes a countably infinite. They are infinite, but they can be countable. But in some way you cannot count the number of uh, number, I mean, you cannot find any function that has one-to-one correspondence with the set of positive integers or the set of the natural number. We call such sets uncountable sets. And one of the classical example is this real number r, right? So our set of real numbers r is uncountable set. Why? What is the real numbers? I will explain it in coming slide as well, but just to give you the introduction. So set of real number capital R is what? So it's starting from the negative infinity, right? And goes on up to having the decimal number values, right? For example, it may have 1, 1.1, 1.1.1, and so on, so on, so on, up to the positive infinity. So in the integers, after one, for example, if it's a set of integer, we can say how many integers are there between 1 and 2. You can say nothing. There is no integer between 1 and 2, and the next integer is 3, next is 4. So we can predict it. But in a real number we cannot do that. So if I ask you how many decimal numbers are there between 1 and 2, so there are infinite decimal numbers between 1 and 2. And again, if I ask you what are the or how many decimal numbers are there in between 1.2 and 1.3, so we cannot say it's the 1.2 point, I mean 1.21122. So infinite number between these two numbers, so we cannot count it. So in such way we call such sets uncountable sets, right? Clear? So when an infinite set is countably infinite, that what I said here, right? So if a set, if it is a countably infinite set, its cardinality is represented with this symbol, right? And we call it elf. This symbol is called elf naught, right? We call it elf naught. And if it is a countably infinite set, so its cardinality is equivalent to the elf naught, right? Or sometimes we call it elf null, right? So that's about the cardinality and the countability. Now let's say how we can show that a set is countable. I have already given you the example, so let's see a few more example. An infinite set is countable, right? If and only if we are talking about the infinite. Remember, finite is already countable. An infinite set is countable if and only if it is possible to list the elements of the set in a sequence. Now this is important. This is important, right? So For example, here stars, can you list them in a sequence? Here from the previous slide, the positive integers and the the even numbers and the odd numbers, can you list them in a sequence? Yes. If yes, then you can only say that it's a countable set. So what is a sequence? We have studied it in the previous video lecture, right? So for if an infinite set is countable if and only if it is possible to list the elements of the set in a sequence. So if we can form a sequence, we can list this set in a sequence, we say that this is the countably infinite or the countable set. So the reason for this is that a one-to-one correspondence f from the set of positive integers to a set s can be expressed in terms of the sequences. We already know that if the a1, a2, a3 up to an are the elements of a set, we can form a function such that this a1 can be mapped to number 1 in the natural number or the positive integer. A2 can be mapped to the with the help of the function to number 2. A3 can be mapped to the A3. An can be mapped to the Fn, right? So with the help of the function, we can map these, we can list the elements, we can list the element of this set, and then with the help of a function, we can map them to the natural numbers or to the positive integers, right? If we can do that, we say that this set is countable. And now by keeping this in mind, we will prove in rest of the examples that whether the set is countable or incountable when it is infinite set, right? Here is a classical paradox, that is the Hilberts Grand Hotel. So this paradox was given by the David Hilbert. So I would like to explain it with the help of a video. So be with me and watch this video, and then we'll come back to the topic.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilberts Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Right. So this is an amazing paradox that was about the Hilbert's Grand Hotel. So that's here you can see there is an infinite number of rooms, but infinite number of the residents and the guests, but they are countably infinite. So if they are countably infinite, we can always accommodate them in some way. So the key is the countably infinite, right? So this is most important thing, the countably infinite number of rooms, the countably infinite number of the guests, and everything. All right, this is just to give you the one example or the classical paradox that how actually this countability and the countably infinite sets are important. Now let's have some examples showing that a set is countable. So the example one is show that the set of positive even integers is countable. Oh, come on. I have already mentioned it in the previous slide, in the slide number 1. So we have the countable, the even numbers 2, 4, 6, 8, 10, 12, and so on. And so this is the set of the even number, that is E, right? And this is a set of the natural number, or let me call it set of the positive integer, right? So for every even number, we can map it to the we can have a one-to-one correspondence with the natural number or with or with the positive integer. So we can easily find a formula. We can easily find a function that is f of x is equal to 2x, right? So that is basically the mapping of even number to the set of natural number. So if we can do that, we will always get the bijection function, or we will always get the one-to-one correspondence. So you can see x, if x is equal to 100, so f of x is equal to 200. So this will be mapped to the to the 200 in the um, or if x is equal to 99, right? So this will be 198. That will be 90 at the 99th number in the set of natural numbers. So we have a sequence, we can map it. So since we can find the bijunction function, yes, this is the countably infinite function. Okay, so show that the set of integers, that is z, is countable. Now this is something interesting. So set of integers, so set of integers may be positive and negative. So what is the set of integer? We already know that that is starting from the negative infinity, right, to so on up to, for example, -2, -1, 0, 1, 2, and so on up to positive infinity. So that's the set of the integers. So what does it says? It says show that the set of integer is countable. So how can we show that? So a very simple way, I'm going to explain it here, and then we'll come back to this whatever is written on the slide. So we are going to map it to the z positive or to the natural number. That is what? That is 1, 2, 3, 4, and so on up to the infinity, right? Clear? So what does it mean? It means, can we list these numbers of the, can we list the integer, no matters whether it is uh, the negative or the positive integer? So can we map it to the natural number in a one-to-one correspondence? So let's see how. So for example, we have some numbers. So for example, -2, we start from the negative, or let's start from the some near to the negative infinity. I can map it to the sequence number 1, the next one to the sequence number 2, the next one to the sequence number 3. This maybe goes to the sequence number 4, sequence number 5. So this always give, I can map it to the one to one correspondence. So you might say that when this approaches to infinity, what happens to this one? This is also approaching to infinity. Since both are the infinite sets, so no matters. So there is always a room when there is the infinity, like we saw it in the Hilberts hotel. So these are the infinite. So if it is about this one, so there will always be a space from this to some particular number, right? So this is how we are going to map it. So let's see now, see what is written over here, how we have solved it. Can we can list this sequence like this: 0, 1, -1, positive integer, negative integer, 2, -2, 3, -3, and so on, right? And then we can map those numbers to the sequence. I mean, we are mapping these numbers. So this is something like something like this is, for example, 0, 1, okay, 0, a1, right? A1, -a1, a2, -a2, and so on. So we can easily map these number to the to the sequence 1, 2, 3, 4, 5, 6, and one, we can have one-to-one bijection. We can always compute, I mean, the function is like this: f of n is equal to n by 2 if the number is the even number, and we can compute f of n is equal to -n minus 1 divided by 2 if the n is odd. So we can always find the one-to-one correspondence. If we can do that, then this set is countably infinite, or this is the countable set, right? So now let's see one example about the rational numbers. What are the rational numbers? Rational numbers are the numbers that is with the decimal values, but they are different from the real numbers. Real numbers are called the irrational number. So the rational numbers are represented with the set q, right? If you remember from the previous set theory, right? So q is a set of all the rational numbers. Rational number, for example, 1 divided by 3, 1 divided by 5, 1 divided, all possible fractions is the rational number. But then there are some fractions that we cannot compute. I mean, for example, the pi, right? For example, pi is not the rational number, it's an irrational number, since it includes some infinite. For example, this is 3.1444, and so on goes on. For example, radical of 2, right, under square root of 2. So this again gives some values that is not rational, that is not countable. So the point value even is not countable. So so such numbers are called the real numbers, that we will see in the coming slide. But the rational numbers are the numbers that has the fractions, right? But we can always compute it like this. A rational number can be expressed as a ratio of two integers p and q such that q is not equal to 0. So q is p divided by q, right? So the rational number is p divided by q such that q is not equal to 0. If q becomes 0, this will become infinite, so a undefined number, right? So we can see how we can represent it. Show that the positive rational numbers are countable. So show, the question is, we need to show that the positive rational numbers are countable. How we can prove it? Now let's see. The positive rational numbers are countable since they can be arranged in a sequence. We can find a sequence for these rational numbers. So that's why we are calling it the countable. How we can find, how we can arrange them in a sequence? Let's see. So what this is a way to organize or to list all possible rational numbers. So what's the way? So for example, this is okay, I'm going to write it 1, 2, 3, 4, 5, and so on. And in this call, row number 1, row number 2, row number 3, row number 4, and row number 5 as well. So what happens? We can list all possible fractional numbers here. We can list all rational positive rational numbers in this table. How? Here you can see this number at this place is basically nothing but the column number divided by the row number. So column number divided by the number. That's why it's 2 over 2 divided by 1. Column number divided by the row number. So here at this point you can see 2 by 3. 2 by 3 is second column divided by the third row, right? 2 divided by 3. So we can list all, and this goes on, for example, 1 by 1, 2 by 1, 3 by 1, 4 by 1, 5 by 1, and it goes on up to infinity. Similarly, it goes up to the infinity in the row wise, right? So we can list all possible rational numbers. Then how we are going to count them and how we are going to list them, we are going to make a sequence of them. It's very simple. So you always start from the first number, that is 1 divided by 1, that is 1. So I am going to mark it here, right? So I am going to make a circle on it, and then we go in this direction. So here you can see like this, right? So that is 1 divided by 2, that is 1/2, and then move on like this, right? And then this is 2 divided by that is 1, and then we go on like this to the um, next number, that is 3 divided by 1, that is 1. And then we come to here, this one, that is 2 divided by 2. But then 2 divided by 2 is nothing but the but 1 only. So 1, we have already listed 1, so we'll leave it. That's why this is not circled. Move to the next one, that is 1 divided by 3, right? And then go on like this one, that is 1 divided by 4, right? Go on the next number. So we can make a list, 2 divided by 3. Go to the next number, that is 3 divided by 2. Go to the next number, that is 4 divided by 2. Come to the next number, that is 5 divided by 1. Then go to the next one. Then this is 4 by 2. 4 by 2 is nothing but 2. 2 is already listed, right? That was already circled. So that's why we leave this. Then 3 by 3. 3 by 3 is nothing but 1. We already listed 1 there, so we leave it. We do not, so you remember, set do not have the repeated elements. That's why we are leaving it. Then 2 divided by 4, that is nothing but 1/2. 1 divided by 2, that we already have in this set. And then 1 by 5, and then goes on. And in this way, we'll move on going, I mean, next, like this, right? And then like this, and we will keep on doing in this way. And we can list all possible rational numbers. Since we can list them, we can have a sequence like 1 divided by 2, 2, 3, 1 divided by 3, 1 divided by 4, 2 divided by 3. From this table, we can always find a function. If this is the rational number q, positive rational number q, we can always map them to the z plus. We can find one function that can map these number to this one in a one-to-one correspondence. So you can see this is one-to-one correspondence, right? If this can happen, we call it countable set. So that this is the infinite set, but the set of positive rational numbers are countable, right? Okay, strings. Show that the set of finite strings S over a finite alphabet A is countably infinite. So this type of questions we will be dealing in coming subjects as well, that is about the theory of programming languages, but this is from the natural language, right? So assume an alphabet ordering of symbols in A. So you have the alphabet, show that the strings can be listed in a sequence. If we can show this, we can list these strings in the sequence, definitely it is countable. If we cannot, then we cannot say that. So all the strings, so how we are going to list them? So we are going to list all the strings of length 0. There are strings of length 0 in alphabetical order. Then all the strings of length 1 in lexicographical order, then all the strings of length 2 in lexicographical order, then all the strings of length 3, and so on. So we may have infinite number of strings over the alphabet A, but we can list them in some sequence. So if we can list them, this implies a bijunction function from the natural number to this set of strings. That's why we are calling it countably infinite set, right? So the strings are infinite, but they are countably infinite. Okay, so the set of all Java program is countable. So how we can show that this set of all Java program is countable? So let S be the set of strings constructed from the characters which can appear in a Java program. So for example, for a Java programming language, uh, how many programs can be constructed, how many software can be constructed, how many programs can be written for the Java programming language? Obviously they are the infinite programs that we can write for a Java programming language, right? But that is that finite program countable if infinite or uncountably infinite? So how we can prove that? Use the ordering from the previous example that we have taken in the alphabet, in the previous slide. So take each string in turn. So feed these strings into a Java compiler, right? A Java compiler, we already know that what is the Java compiler. So a Java compiler will determine if the input program is syntactically correct Java program or not. So the compiler, if you write a program, list all the possible Java programs, compile them. If they are syntactically correct, their syntax is correct, so that is actually the Java program. So if the syntax is wrong, so you simply discard it. If the compiler says yes, this is syntactically correct Java program, we add the program to the list. If the program is not syntactically correct, that means Java is not, that does not belong to the Java programming language. So we move on to the next string, and we'll make a list of such programs. So in this way we construct an implied bijunction function from natural number n to the set of Java programs. So hence this set of Java program is countable, right? Okay, so the real numbers are uncountable. So as I mentioned earlier, the real numbers are uncountable because between the real numbers, for example, the pi, right? Let me give you what the example of the pi. So the value of the pi, we already know that that is 3.14 through so to and up to the infinity, and then this is just between the 3.14 and 3.15, right? So between these 3.14 and 3 and 15, we have infinite numbers. So since it is the infinite numbers, infinitely I mean, this is we cannot map these numbers to the natural numbers. That's why we say that this is uncountable. But how we can prove that this is uncountable? This, we cannot map this number to the to the natural numbers or to the positive integers. For that we use a diagonalization method, right? So the method to prove this is called the diagonalization method, and we always prove it by the contradiction, right? So what we do actually, we form a diagonal method. So for example, I have a value of some value of some I mean, like some some table that we created in the for the rational numbers q, right? Similarly, I can construct a table for this one. So for example, this is point some number point 3411432, right? uh, and then there is a number point 1 2 3 1 2 4 1. There may be some number like 0.2193112. There may be one number 0 0 1 1 0 2 and so on, right? These all are the infinite, right? Infinite, and this keep on going infinite in both directions. So what does diagonal method says? Diagonal method says choose the diagonal numbers. Diagonal numbers, right? So diagonal number is this one, right? So choose the diagonal number and construct a new number, right? Construct a new number, like for example, by adding or subtracting some number from these diagonal numbers. For example, for this 3, I am going to make it, for example, 4. Sorry, 4. For this 2, let me make it 3. So point is there, right? 0.43, and then 9. Then okay, this is 9, so I am going to make subtract 1 from it, 8. This is 1, I may add 1, and that's become 2, right? So since this is the continuous in up to infinity, this is also up to the infinity. So I have constructed this number. So now, if this number that is newly constructed belongs to this table, can I find this number from this table? If yes, then I can say this number is already part of this table, and this is already counted. But then you will see such number that is produced with the help of this table is not part of this table, right? So that means there are many numbers that are left that are not presented in this table. So that means we cannot list all the real numbers in any fashion, in any table, or in we cannot list them. We cannot have a sequence of them. We cannot make a sequence of the real numbers. So that's why we say that this real number r is uncountable, right? So that's what we have written here. This whole process is written over here. You can read it. So but in a nutshell, the r is uncountable because this method is called diagonalization method. From the diagonal numbers, produce a new diagonal number, and then prove that this number is present in this table. That is actually not. So that's why this is uncountable, right? Then computability. So we discuss about the cardinality, countability, right? So countable finite sets are countable, infinite sets may be countable, and if they are countable, we call it countably infinite. They may be uncountable, that is called infinite uncountably infinite, right? So what is computability? Computability deals with the computations, right? So we say that a function is computable, right? We are talking about the function f of x. Remember from the previous, the whole, we discussed a lot about the functions. So we say that a function is computable. And by the way, in this video as well, we are saying that we need to find a function that maps this set, the elements that we are going to find the cardinality. We are going to map those elements to the set of natural numbers or set of the positive integers. So we are interested to find a function, right? So but then whether this function is computable or not. So we say that the function is computable if there is a computer program in some programming language that finds the values for this function, right? If the function is not computable, we say it is uncomputable. So remember, all the functions are not computable. So that you will learn in detail in theory of computation or theory of programming languages, as well as in analysis of algorithm. So all functions may not be computable. So only those functions are computable. For that we can have a computer program, right? Okay, so one of the example, just to give you you can explore it further. Hilbert's 10th problem. Just Google it and you will find the Hilbert 10th problem, and then that is the uncomputable, right? Okay, there are uncomputable functions. As I told you, we have shown that the set of Java program is countable. Yes, set of Java program is countable. We know that. So exercise in the exercise, there are some functions that are uncountable, and I mean, you obviously if they are uncountable, So how it is be the countably infinite, right? So there must be some uncomputable functions as well for the uncountably infinite functions, right? So for the uncountably infinite functions, the functions are not computable, uncomputable. All right, so this is about today's video lecture. So what we studied here, only three concepts, but in very detail. One is the cardinality. We revisited the cardinality. We talk about the computable countable sets, countability, and we discuss about the computability. So in the next video I will be talking about the matrices. You already are very much aware with the matrices, so I may not go in much detail, but wait for the next video. Until then, prepare your questions, and then we will talk about it in the coming Zoom meeting. So until then, take care and bye bye.